Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 5 on reactions catalyzed by organometallic compounds. In this video, we will discuss the Monsanto process and its mechanism with electron count. This video will be helpful to JAM, NET JRF and GATE aspirants. This video is also as per the syllabus of MSc final year students for inorganic chemistry. First of all, let us introduce the subject. The quick-vinegar process has been the classical method for the manufacture of vinegar by aerobic bacterial action on the dilute aqueous solution of ethanol. The quick-vinegar process is a classical method for the manufacture of vinegar, and this process involves the aerobic fermentation of aqueous solution of ethanol in the presence of aerobic bacteria. Dilute aqueous solution of ethanol is subjected to aerobic fermentation in the presence of Mycoderma acetobacteria at 35 degrees centigrade and 1 atm pressure for 7 to 8 days. As a result, we get dilute aqueous solution of acetic acid, which is called vinegar. Vinegar is the dilute solution of acetic acid. It contains usually 4 to 6% of acetic acid. But this method is uneconomical for the manufacture of concentrated solution of acetic acid in industries. This method is suitable. This classical quick vinegar process is suitable for the manufacture of vinegar, but it is not suitable for the manufacture of concentrated solution of acetic acid in industries. The chemists at Monsanto of Italy developed a catalytic process for the manufacture of concentrated solution of acetic acid by direct carbonylation of methanol in the presence of rhodium catalyst RH CO2 times I2 minus. This catalyst is used in this process, which was developed by the chemists at Monsanto of Italy, and this reaction involves the direct carbonylation of methanol in the presence of this catalyst. Methanol is treated with carbon monoxide gas at 180 degrees centigrade and 30 to 40 atm pressure in the presence of this catalyst in very low concentration, 10 to the power minus 3 m, and we get concentrated solution of acetic acid. This reaction, which involves the carbonylation of methanol, produces conc solution of acetic acid, and this rhodium catalyst is used in this process. The rhodium complex catalyst developed at Monsanto greatly reduced the cost of product, that is acetic acid, by allowing the reaction to take place at lower temperature. The cost of acetic acid produced by this method is low because the catalyst is very efficient and it allows the reaction to take place at relatively lower temperature and pressure. Importance of Monsanto process. present more than 2 million tons of acetic acid is manufactured annually by this method throughout the world. This process is highly selective and it generates acetic acid with such a high purity that it can be used in the human food. It is also used in the manufacture of vinyl acetate, cellulose acetate, and other esters, pesticides, and many other chemicals. Feature of catalyst used in Monsanto process. The catalyst RHCO2 times I2 minus used in Monsanto process is a tetra-coordinated square planar complex of rhodium-1. It is dimagnetic, having no unpaired electron, and its electron count is 16. This is the square planar complex RHCO2 times I2 minus charge, which is used as catalyst in the Monsanto process. Its shape is square planar. Coordination number is 4 because RH plus ion is bonded to 4 ligands. Oxidation number is +1. Electron count is 16. Magnetic property dimagnetic. It has no unpaired electron. The oxidation number of rhodium is +1 and its electron count can be calculated as follows. 9 electrons are present in the valence shell of rhodium atom, -1 for +1 oxidation state, and each of the 4 ligands contribute 2 electrons to the electron count, and accordingly the total electron count is equal to 16. This complex compound of rhodium +1 is coordinatively as well as electronically unsaturated, and hence it is a highly active and highly efficient catalyst mechanism. The Monsanto acetic acid synthesis consists of following steps. In the first step, there is oxidative addition of methyl iodide on the catalyst as follows. This is the catalyst and methyl iodide undergoes oxidative addition on it. It is a slow and rate determining step. The rate of reaction, overall reaction, depends upon this step. As a result of this step, the oxidation number, the coordination number, and electron count of the central metal ion all increase by 2 units. Oxidation number, coordination number, and electron count all increase by 2 units. The oxidation number is +1 in the reactant, but in the product the oxidation number is +3. There is increase of +2 in the oxidation number. The coordination number is 4 here. 4 ligands are attached to RH plus ion, but in the product the coordination number of RH triple plus ion is 6 because 6 ligands are attached to it, and the electron count, as we have seen earlier in the catalyst, is 16, but in the product the electron count is 18. It may be calculated as follows. 9 electrons present in the valence shell of rhodium atom, -3 for +3 oxidation state, and each of the 6 ligands contribute 2 electrons to the electron count, and accordingly the total electron count is equal to 18. And in the second step, there is migratory insertion of coordinated CO into RHCH3 bond. The CH3 group of the complex formed in the step number 1 migrates to the coordinated CO ligand within the same coordination sphere, it is called migratory insertion reaction. Let us see. This product was formed in the first step, and one of the coordinated CO undergoes insertion reaction into RH-CH3 bond. But in actual practice, the methyl group migrates to the coordinated carbonyl group present adjacent to it. As a result, of this migratory insertion reaction, the electron count of rhodium decreases by 2 units, the coordination number decreases by 1 unit, and thus a vacant coordination site is produced along with an acyl complex. Due to migration of this methyl group to the coordinated CO group, the CO group transforms into acyl group, and a vacant coordination site is produced here. The coordination number is 6 here, but in the product, the coordination number is only 5, and it has a vacant coordination site. The electron count of the CMI in the product, 9 electrons present in the valence shell of rhodium atom, -3 for +3 oxidation state, and each of the 5 ligands contributes 2 electrons to the electron count, and accordingly the electron count is 16. It is electronically unsaturated as well as coordinatively unsaturated. CO coordination. The 5 coordinated 16 electron acyl complex formed in a step number 2 attracts a CO molecule from the reaction medium, which occupies the vacant coordination site, and thus an 18 electron species is restored. This is the vacant coordination site, 5 coordinated acyl complex. This is acyl group, acetyl group in particular, and this 5 coordinated electronically and coordinatively unsaturated intermediate attracts a CO molecule from the reaction medium to the vacant coordination site, to which CO molecule gets attached to RH triple plus ion, regenerating the 18 electron species, which is electronically as well as coordinatively saturated. Let us see its electron count. 9 electrons present in the valence shell of rhodium atom, -3 for +3 oxidation state, and each of the 6 ligands contribute 2 electrons to the electron count, and there is total 18 electrons in the valence shell of rhodium atom. It must be noted that all these electron counts are as per the ionic model of electron count. There are 2 models for electron count. One is ionic model and other is covalent model, and both the models give the same result, but only the approach of calculation of electron count is different. Reductive elimination of acetyl iodide. Reductive elimination of acetyl iodide. The electronically and coordinatively saturated intermediate produced in the step number 3, this one, undergoes reductive elimination of acetyl iodide molecule, regenerating the original catalyst, that is RHCO2 times I2 minus. This intermediate, which was electronically and coordinatively saturated, produced in step number 3, undergoes reductive elimination of acetyl iodide molecule, acetyl group and iodine atom from cis position, are eliminated in the form of acetyl iodide, and thus the catalyst is regenerated. In this reaction, the oxidation number, coordination number, and electron count of the CMI all decrease by 2 units. The coordination number is 6 here, but the coordination number is only 4 here. The oxidation number of rhodium in the reactant is +3, but in the product, the oxidation number of rhodium is +1. The electron count is 16 here, but not 16 not. The electron count is 18 here in the reactant, but the electron count in the product is 16. Thus, we see that the oxidation number, coordination number, and electron count of the CMI all decrease by 2 units, and this is the characteristic feature of reductive elimination reaction. The oxidation number is +3, coordination number is 6, and electron count is 18, but in the product the oxidation number is +1, the coordination number is 4, and electron count is 16. Thus we see that all decrease by 2 units. And in the fifth step, there is hydrolysis of acetyl iodide produced in step number 4. The hydrolysis of acetyl iodide produces acetic acid and HI. This is acetyl iodide. Its IUPAC name will be ethanoyl iodide, and it undergoes nucleophilic attack by H2O producing acetic acid and HI. Actually, this reaction is nucleophilic substitution reaction in which iodine atom is replaced by nucleophile OH. And in actual practice, this reaction proceeds through addition-elimination mechanism, and overall it is a nucleophilic substitution reaction. And in the final step, generation of methyl iodide from methanol and HI. HI produced in step 5 is used to produce methyl iodide used in step number 1 by the reaction with methyl alcohol. Methyl alcohol reacts with HI produced in step number 5, producing CH3I and H2O. On adding all the above 6 steps, the following overall reaction is obtained. Methanol plus CO produces acetic acid. It is the carbonylation reaction of methanol producing acetic acid. The catalytic cycle for Monsanto process is depicted on the next slide. This is the catalyst, rhodium catalyst, on which methyl iodide undergoes oxidative addition reaction. As a result of this oxidative addition reaction, the electron count, the coordination number, and the oxidation number of the CMI all increase by 2 units. Then there is migratory insertion reaction of CO into RHCH3 bond. During this reaction, CH3 migrates to adjacent carbonyl group, producing a vacant coordination site, and this vacant coordination site is occupied by CO molecule from the reaction medium, and as a result of this migratory insertion reaction, we get acyl derivative of metal, and this acyl derivative of rhodium +3 undergoes reductive elimination reaction, liberating acetyl iodide, acetyl group from here and iodine atom from here. this acetyl iodide is liberated and the catalyst is regenerated. Acetyl iodide undergoes hydrolysis reaction, forming acetic acid, which is the desired product, and HI. And this HI is used to transform methyl alcohol into methyl iodide, which is the reactant in the first step of Monsanto process, and thus the catalytic cycle is completed. Rhodium plays its role nicely due to two reasons. Rhodium exhibits variable oxidation states +1 and +3 of comparable stability, which differ by 2 units. Rhodium has one characteristic feature, that it exhibits variable oxidation states +1 and +3. These two oxidation states of rhodium have comparable stability and they differ by 2 units. Rhodium oscillates between these two oxidation states during Monsanto process. During Monsanto process, rhodium oscillates between these two oxidation states +1 and +3, which differ by 2 units and have comparable stability. And at the same time, rhodium can acquire two coordination numbers 4 and 6. And due to these two reasons, rhodium plays its role nicely during Monsanto process. I- ion is the best anion for this catalytic system, again due to two reasons. The first one, methyl iodide undergoes oxidative addition reaction to the catalyst at the greatest rate in the rate determining step of the reaction. And the second one, I- ion is a soft Lewis base and it is a good ligand for RH1, which is also a soft Lewis acid. It is in accordance with the soft and hard acid base principle given by R.G. Pearson. I-, which is a soft Lewis base, has a tendency to combine with RH plus ion, which is also a soft Lewis acid. A soft Lewis acid and a soft Lewis base combine together, forming a relatively stable adduct, and this is why I- ion is the best reagent in the Monsanto process, best anion, best nucleophile in the Monsanto process. Thank you for watching the video with patience. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.